Firstly, hello to everybody. I've worked with the Turkish aerospace industries. I've been working here for practically 25 years, and we've been working with many different airplane brands. And as of the beginning of 2013, I worked in aeronautic, and now I'm working as senior expert, and I'm trying to help the young people so that they can learn the market. Would you like me to speak in Turkish or English? Because when we make these presentations, we do them in English, obviously. That's why I had prepared this presentation in English. And that's why it's English, because I had made this presentation in Stuttgart. As you know, assembly lines, especially in the airplane industry, in the aircraft industry, there is a lot of intensity. Everything comes together in the assembly line. There's always very lack of time. You have to solve all these problems simultaneously, and many problems which had not occurred to you before may actually arise. And one of the most important impacts is time, because you're racing against time. These photos that you can see, of course, we don't produce F-16s anymore, but you can see a few assembly lines of F-16 airplanes. It's like a beehive, especially if you are producing an aircraft. I had the opportunity to see other assembly lines. People are actually working like bees, and there's a lot of hustle and bustle, and it's very difficult to actually solve the problem. And if the problem has arisen at that moment in the assembly line, there is a lot of cost problem, and because of time issues, you actually hear a lot of complaints from the customer. Of course, now we think that the rate of composite usage will actually increase. We talk about composite aircraft. There really is an increase. During the 1990s, for example, what we termed a secondary structure, that's where the composite materials were used much more. But now, composites are all around the aircraft, all parts of the A380, you know that it is one of the first aircraft to use composite material, and it's about 25%. Now, Boeing 787 Dreamliner, the composite material is about 50%. 50% of that aircraft was made of composite material, and composite, of course, it has a lot of advantages to use composite material, but there are also disadvantages. Let's talk about these. Now, when you use composite, for example, your production lines need to be much more rapid. They need to be much faster. Airbus, for example, the sales rate monthly is about 100. So in many places around the world, there are actually countries that produce the 320, the aircraft 320, and you have to produce 18 of these on a monthly basis so that you can give it to those people, to those customers. And if you want to get more business, you have to be fast anyway. You have to work with advanced technology, especially if you want to work on an international basis. These are all your musts. Okay, we said composites, especially in the aviation sector, it really is a driver. And the technology, of course, is very high-tech in the aviation sector. Why is there a trend towards composites? There is what we term as high strength-to-weight ratio. The fibers, the directions in the fibers, and the stacking, the direction of the stacking within the fibers, you're able to actually make use of that, which enables you to have much more lightweight products. And when the composites when the weight is less, that proves to be an advantage. It's about 20% in A320 in terms of the weight. And if an aircraft is actually using 20 20% less fuel, it means it's going to carry 20% more passengers, and because it's going to be able to carry more fuel, it's going to be able to go to longer distances, etc., etc. So just about all of the metal aircraft is actually orientating towards composite material, but on a long term, I think that all of the aircraft, that the composite components will increase in the aircraft that is being used. What we mean by single one-shot, rather than producing many small parts, you have one huge complicated part, and you actually are able to do this with composite material, and the mold is very important at this point. One of the most important handicaps of composite is the composite tools. You know that I'm going to talk about this tool issue later on in my presentation, but actually you have the opportunity to produce much more gigantic pieces, parts rather. And the life cycle costs, the part actually does have a much longer life cycle, and the cost, and as a result of this, the cost maintenance is much easier. And you don't really need to have a lot of maintenance. You don't need to follow it all the time. You don't need to measure it all the time. Corrosion and fatigue resistant, that's one of the main reasons why composites have actually been used in aircrafts in the first place. In F-16, the aircraft, there was a serious issue of corrosion in the fighters also. And of course, we're not able to talk about that right now. But anyway, but the corrosion and fatigue resistant and this feature of composite is very important. But even though we're able to say, okay, composite material is really good in terms of corrosion and fatigue resistant, there are other problems because composite, with time and with humidity, it actually loses a lot of its important features. And we, of course, have very special kilns and what we term as aging, obviously. We actually age this material beforehand, and we have to see whether we're able to still receive the same performance from that material or not. I don't know the other sectors so much, but I know our sector, in the aircraft sector, when the composite is first produced, the performance of that composite material when it's first produced in comparison to 20 years later, after it has been subject to humidity and heat, unfortunately, they do not have the same performance, or they may not have the same performance. What are the disadvantages of composite parts? Okay. You don't really have the chance, or you don't really have the opportunity to repair a composite part. And if it has any kind of problems, if it doesn't work anymore, you sort of just, well, throw it out, basically. And it's only in very small or incidences that you're able to actually do what we term as cosmic repair. And of course, the designs, when it is designed, that's how it is designed. It's designed so that it is able to continue its life cycle if it has a few small problems. But it's not like metal, for example. You can break it, you can put in another material, etc. But with composite parts, you don't really have that. Another problem is the delaminations, for example. These are serious headaches, by the way, because those are really small problems, because they cause problems in the future in terms of delaminations. You end up having to throw that composite material completely. If you will accept us, we will listen to you standing up. I wasn't actually expecting so much participation, because last time I spoke at a conference, there were only 4 people listening to me. Should we go out, says one of the participants. No, of course not. Okay, you need to come to the composite symposiums, obviously. Okay, so what we term as manufacturing defects, because they cause elimination. Of course, this is relevant for all kinds of structures, for all composite material, and it is a very important issue that we have not been able to prevent as yet. So if you have not been able to define your process, if you're not sure of your process in terms of your composite, you have to have internal inspection for sure. That is a must. And it's obviously not a cheap process to have this internal inspection. The technicians need to be trained, they need to be found. They're all very sensitive matters that need to be taken into consideration. Do we have this in Turkey? I think one of the participants asked. Yes, we do, especially advanced people or places rather that use advanced technology. Yes, you can find these kinds of processes. We said that the non-recurring costs was high. The design of composite material is difficult. You have to actually analyze many different aspects. In metal, on a world scale, everybody knows what's going on, basically. They know what they're going to calculate, what they're going to design, and they know what they're going to end up with as the end product. But that is not the situation with composite material. The processes change, the calculations change, and for all of this to be accepted, it's actually not that easy, which means that a lot of analysis needs to be held simultaneously by people who are experts in their field, especially in the aircraft sector. Mistakes cannot be forgiven or accepted in any way. Machine engineers would know this. They call it margin of tolerance, for example. Boeing people speak differently. Airbus people speak differently, but this margin of tolerance is very low. And tool is very expensive. We use a material that is called invar. It's very expensive, so the non-recurring costs of composite material is quite high. Of course, as time goes by, we think that the cost will decrease as it is used more and more. Okay, assembly challenging. People who deal with composite materials, who produce composite material, would know this, that there's always a spin back effect. It never ever really 3 millimeters, 4 millimeters from the edges, from here, from there. Definitely, it will have a different shape. You can never really produce what you thought you would produce in the beginning. These variations actually change between 4 and 7%. We call this spring back effect under normal circumstances. So in order to make sure that we don't have or we don't experience this spring back effect, what do? We produce it in the beginning. We see the variation degree. We actually give the tool some kind of mobility, some kind of movement, and we see what happens. And this is actually quite a difficult and highly costly issue. This spring back effect, I think, needs to be taken into consideration when this composite material is being produced. Tolerance stack up, spring back impact, especially we usually work on aerodynamic surfaces, but the tolerance stack up is very problematic in these kinds of surfaces, and they need to be managed in some way or another, so they actually need to be foreseen. And these are really the main trouble for our sector, and it will kill you to have to deal with this problem. That's another disadvantage. I will actually talk about this a little bit more further along my presentation about tolerances stack up. As you all know, electrical and thermal conductivity is very minimal for composite material. I think precaution needs to be taken relating to this issue. We actually have some design recommendations which could help to deal with this problem. Design data, that's a serious issue, because there are very few people who know this, and it's very difficult to actually reach or access this data. What is the allowability of this material? And etc., etc. It's really difficult for you to reach this kind of information. Everybody who actually works in this field, they produce their own knowledge and they hide it like as their own know-how. So this is not a world wherein this kind of knowledge or wherein this kind of information is shared. So we need to also produce this know-how, and yes, we need to also maybe hide it and keep it a secret from others. But we need to, both in the aircraft and automotive sector and energy, we see that composite material is being used in all of these different sectors. Damage tolerance, maybe some of you don't know what damage tolerance is. Damage tolerance, when you have any sort of impact, these impacts are actually dangerous because you should not have an impact on composite material. You will not see anything from the outside. It looks very nice and clean surface, but inside there could be some kind of deformation which you may not be able to observe and which you probably will not be able to observe. So the deformation will actually be growing inside. We have certain damage tolerance tests, and this is actually a completely different field now, and this is very, very important. What is the allowability? To what degree can that composite material actually accept the impact, etc., etc.? Because sometimes you think nothing has happened, but really, as I said, under the surface, many things can actually be festering, and that could cause serious problems. This is, I think, one of the most important issues regarding composite materials. Right now, we're working on some resins. There are certain people who are also working in EU commissions, etc. I think that this is one of the issues that will be solved in the near future, for resins to be more flexible so that they can be more impact resistant. Again, two photos from an assembly line. This is a 350. You can see the fittings. These are metals. We still have not been able to get rid of these metals. And there's a composite surface. I will be talking about this in a few moments, but this is a problem that we need to solve. And this is a 400, the main body, the assembly line for the main body of the aircraft. We talked about this. Assembly means cost, assembly means money, assembly means time, the assembly line. And naturally, the processes in the assembly line need to be extremely simple. It shouldn't be, we need to put that over there and we need to fit that down there, etc. No, no, no. The assembly needs to be as simplified as possible. Especially in the aircraft sector, the most important issue is weight. That's the most important issue. It's one of our main drivers. So, if you want to decrease the weight, you can't do anything in the assembly line. It's too late to deal with the weight issue on the assembly line. You need to think of this beforehand. Interface, sometimes it can be termed as interface management. We usually talk about the large parts of the aircraft coming together. All kinds of large parts coming together in the aircraft sector is defined as interface and interface management. And there are different departments. People actually try to manage these departments by dividing them. But as I said before, tolerance is very important. There are two types of tolerances, 1D and 3D, two different types of tolerances. In 3D, obviously, all kinds of directions, all kinds of impacts, they're all taken into consideration, and you have to make the analysis, and you have to do this at the design stage. Otherwise, there's no way you can actually get away or escape a problem from rising. So the design, when it's being detailed, all of these issues need to be dealt. So I think that tolerance is a part of the design level, the design stage, especially if you're thinking of and if you are working with composite material. What do we do in these activities, in the tolerance analysis? we try to foresee what kind of a material, composite product we will have in our hands, especially in the aircraft. You have aerodynamic tolerance, obviously, manufacturing tolerance. And on an aircraft basis, all these tolerances are taken into consideration and they are broken down to the smallest part. So when you're designing a part like a composite material, you know what the tolerance is for that part, but it's not very easy to capture that because production technologies, especially the production technologies, is not very suitable in terms of actually capturing what that problem could be. This is a serious challenge. What the plus minus, how much it needs to be increased or decreased. This is a very important issue on an international scale. I try to give an example here. Aerodynamic tolerances, assembly tolerances, manufacturing tolerances, and tooling. Actually flight tolerances, because during the flight there is a certain kind of flexibility in terms of the aircraft and they need to be in harmony with one another. Especially 3D tolerances, of course, you cannot calculate them manually. Nobody can do this. There are special tools. MakerMaster, that's the kind of tool that we use. This MakerMaster is actually a tool that needs special expertise. And with these tools, then you are able to calculate the tolerances on the assembly surfaces. I actually do recommend them. I think it would actually be very good for the automotive sector also. I don't know how necessary this tolerance analysis is for you in the automotive sector, but we do have such a tool. And we also have a shimming, a concept that we term as shimming. It is not actually a structural part. It is just a specially produced material to fill in the gaps. And even though it does not really have any specific use for the structure, it's actually about 2 to 4% of the total weight. The sort of using some kind of a resin or something that is similar to a resin, you fill in these gaps, especially in the assembly line, because as I said, you're competing against time. We need to get rid of this. Shimming, you actually put on, as I said, some of that material, which is sort of like resin, and you have to wait for it to freeze, and then you have to connect it, and it actually causes an extra weight, which is a situation that we do not want. Especially for parts with 2.5 millimeters, up to 2.5 millimeters, it's okay for there to be a gap of up to 2.5 millimeters. But out of this 2.5 millimeters, only 1 millimeter is the part that you can actually fill with shimming. The rest you put another material. Of course, you could be thinking to yourself, do we really have to fill these gaps? Can't we just leave them as they are? We could, but that will mean the weakening of the structure. So, hence, especially in aircraft, there shouldn't be any gaps anywhere. That's why we try to fill all those gaps. And when you look at it overall, as I said, it actually takes up about 2 to 4% of the total weight. So let's say you have 100 kilos, an aircraft which is 100 kilos, let's just say. 2 kilos, 4 kilos is just because of this material. I would like to show you this. I showed you the fitting issue a few slides before. This is where the parts are connecting. You can see the shimming in the photograph right now. Of course, if you have a one-shot, if you have a huge or a larger one-shot part, then this shimming is also decreased. When you look into this 3D tolerance analysis, then you're able to know what exactly the amount is, and you know what the gap is going to be exactly. Then we have another concept, which we term as assembly load. When you try to actually fit a part, there's always some kind of a load left, a residue load. This is quite a new concept, as a matter of fact. We didn't really calculate this before in the past. But what really happens here is
buradaki olay şu. Bu bir aileron assembly'si. Aileron assembly'sinin hinge line'ından şuradan takmaya çalışıyorsunuz.
so you're trying to put the part in here, and according to the hinge line, you see the bearings, and that's where the bearings are fitted. In that zone, there is an extra load which you have not actually calculated. It doesn't come from the aerodynamics. And you need to take this into consideration. Otherwise, this accumulates and it actually causes some sort of damage for the part. And these assembly loads, we actually calculate them during the design phase. And this has about 5% increase in the load, in the total, because usually the load that we have calculated initially has increased a little bit more. Well,
Şimdi yok. O yüke maruz kalacak. Kabulünden giderek hesaplıyor. Çünkü
we
oraya nasıl takılıp takılmayacağına şu an
make these calculations taking into consideration that there will be some kind of load, that it's going to be subject to a certain amount of load. We say, okay, this is going to be fitted to that, or this bearing is going to be connected to here, and that's going to cause so much and so much, for example, load. That's what I meant when I said we calculated at the design phase. Okay, let's talk about fasteners. Actually, fasteners and composites don't really like one another, because to have a fastener, you have to have actually a hole. You have to have some kind of a hole. And if you use some kind of a tool which is not very good, then there's going to be a problem. What we want is to stick composite materials. That is what is desired. That is one of the main advantages of composite material. But unfortunately, we have not been able to do this. Yes, there are certain places where this is accomplished, especially with laser technology. But right now, in terms of the prevalent today's technology, unfortunately, we still have not been able to get rid of fasteners. It is an extra load, it is an extra cost, and with, you know how we said with composite material there is no corrosion, but if you're going to use some kind of a fastener with composites, let's say you can't use an aluminium, for example, with carbon fibers, there's definitely going to be a corrosion. Even if there is no corrosion on the composite material, there is going to be corrosion on the aluminium. That's why you need to use titanium, and titanium is very, very expensive. And with steel fasteners, for example, usually it's not with the design, but it's actually used not during the design phase, but just in case there is a necessity for repair later on. That's why decreasing the amount of fasteners or trying to get rid of them, if you have a large part and if you have the less amount of parts that you have to connect to one another, the less fasteners that you're going to use, obviously. Okay, we say we stick them, but sticking is not actually accepted with according to certification authorities, and they say that you have to have fasteners. We call them, for example, the bonding design approach, and that we use what we term as chicken fasteners, and you need to support these parts, and this is a requirement of the whole certification process. The authorities do not actually accept the safety of that connection if you do not use these fasteners. I talked about manufacturing defects. I mentioned it before.
Biraz önce bahsetmiştim. Kompozitlerde çok fazla.
With composites, I remember I said we don't really have a lot of room for repair. Okay, let's say we produce a single large part or one shot. And when you actually make the part bigger, if there is a problem, if what we term as manufacturing defect, if there is some kind of a mistake, then you have to throw out all that large part, and that's a serious disadvantage. Obviously, there is a serious difference in terms of the price between the small parts and the large parts, because composite material is not cheap. If you're going to produce a large part, you need to make sure that you test the processes with small parts. You need to be sure of your process. The temperature it needs to be matured, it needs to be heated. And after you test your processes with many small parts, then you should produce a few large parts, and then you should be sure that there aren't going to be problems. Otherwise, if you don't do this, there are going to be serious problems which will arise in the assembly line. And especially for my colleagues, for my friends who are taking time into consideration, they need to make sure that they hold all these tests. Of course, this was actually a presentation about weight. We have an observation. We used a nut. I haven't been able to. She's just highlighting it right now. And they have the same specifics, same features with the titanium nuts, the same corrosion aspects. And when we actually merge these two, we have a weight here. And with 1,000 fasteners, of course, according to grades, the smallest grade, we took a mean actually. And in 1,000, we said this kilograms, 11.34. And you think, wow, that's good. But no, it's not actually. Because when you use titanium, your cost increases 6 times. So you have to make a decision. Is it cost? Or is it weight? And you can't obviously invest all your money in these fields. Then you have the problem, or you have the issue of making profit, or your profit margin actually becomes decreased. So when you're trying to decrease the weight, you have to spend a lot of money. But let's say you did spend a lot of money and you still have not been able to decrease the weight, then you lose your competitiveness. This was just a very small example. With composites also, with composite material, there's many ways that you can resort to in order to decrease the weight. But this is all, as I said, about money and time. So if you invest everything in order to decrease the weight, that would be a big mistake. You need to try it in different aspects, and then you should actually move on to using it with the aircraft. We've done this, believe me. I know what I'm talking about. I'm telling you this from the bottom of my heart. Electrical conductivity, we said composites are poor conductors of electrical current. How do we measure them in aircraft? We actually segregate the airplane to zones. Of course, lightning strike, it's very important. That is one of the most important issues and one of our main fears when we're talking about aircraft. You can be sure that each aircraft, every 3,000 hours, or let's say every 3,000 flights, there is definitely a lightning strike that actually hits an aircraft. Believe me, no aircraft can escape from this. I'm sure maybe some of you have even experienced it, but of course there are many precautions which are being taken at the design phase. As I said, we divide the aircraft to zones. 1A, 1B are the areas where the lightning will strike. The highest probability of lightning striking. B is 3B, 3A and 3B is where there is the least probability. And when you actually make the design according to the zones, you of course have to make sure that these panels have been tested. You cannot understand any other way. This panel that you use here, it's a 1.5 meter to 2.5 meters. Unfortunately, in Turkey, we don't have a laboratory for this. For a lightning strike test, we have to send it overseas. We need to send it to another country, and then you are able to check whether your panel has worked out or not. For lightning, we use some kind of material, obviously, and we have copper and bronze meshes. Maybe some of you know about this. I don't know whether this is general knowledge, but with this bronze mesh and copper mesh, which are actually laid on top of the composite, conductivity is given to the composite material in 1A, 1B, 2 times, 3 times. So we have all this mesh which is spread out. Of course, this is very important weight again, but because with composites there's nothing else you can do. You have to do this. There is some new studies, conductive paint, conductive resins. A company in the United States used it for 787. They've actually also taken the patent as far as I know. But the paint, the efficiency of the paint is not really good. We haven't been able to solve it, so we are, for now at least, continuing with this mesh method, which I just explained. This issue of lightning strike, and because of the precautions we need to take, there is an increase in the weight of the aircraft ranging from 1.5 to 5%. So sometimes it can be 1.5 kilos, sometimes it can be 5 kilos, but this is a precaution which you must take. Now, composite. About composite material being produced so that they are conductive. There is some studies, there is some actually work which is taking place in the EU. I'm following one of them especially very closely, and we have the opportunity to enter one of these projects as an industrial partner, but this is an important issue. A solution must be found. Of course, when you find, let's say, you need to have some kind of smart designs. Also, it's not just the copper and bronze mesh that I mentioned. This is an Elroy surface, flying control surface. So it's a flight surface basically, and we actually add parts. So this is where the lightning has the highest chance of striking. So once the lightning actually does strike that zone, by the way, you need to throw it away. There's nothing else you can do with that part. The most important thing is when that lightning strikes, the aircraft needs to land safely as soon as possible, and there's nothing more you can do with this part. Then if you take that part, if you just throw that part away, you can save the rest of it, which means, of course, that it is much more cost efficient. We talked about paint, you will remember. I know nobody really takes a lot of notice of this, but paint is really important because it also adds a lot to the weight, because it's about 600 kilos, for example. And it's not just, you don't just put the paint on top of each other. You need to have the primer paint first, especially for composites, so that it doesn't age, so that you're able to protect composite material from external forces, from aging. There is a specific process you need to follow in terms of the paint, and that actually brings on an extra weight. Of course, there are many studies also being continued in this field. But paint is one of the factors which means that the weight is going to increase. Now, especially if you are producing a composite, an L-shaped composite, here at the part that I'm showing you, there is a problem which we term as unfolding. All of a sudden, in this unfolding, all of a sudden, really, really rapidly, delamination begins. And after it begins, you just cannot seem to stop it, and you just need to throw it out again, once again. And you need to, the radius needs to be as wide as possible. Especially if the radius is narrow, then you have this unfolding problem much more. Of course, this really is a problematic issue. The minute you have a tensile test, for example, it goes away. If this actually took place while the aircraft was flying, it could even mean that the aircraft actually falls. I'm sorry, I can't hear the questions when they don't use a microphone. This L-shaped ultrasonic inspection, you don't really have the possibility to see this scanning method or X-ray method. I think he said X-ray method. So there is because I only look at the radius, that's all. If it's a wide radius, you don't really have this problem, but if it's a narrow radius, you're not able to see, or you're not able to observe that this problem is going to take place. We have new material which is quite suitable to composite material, aluminium lithium. It's quite a new material. It's used especially for 350 Airbus. They've actually sort of forced the suppliers to use this. But the problem with this is the corrosion and the fatigue features are very, very good of this material. But the main problem is it's very, very expensive, and you can only have an export license. I wish we had the opportunity to produce this kind of material in our country, because we are not able to produce it in your own country. You become dependent on overseas suppliers, and the material needs to be processed differently because it is sometimes able to explode. It's not very safe. But especially the aircraft companies, they seem to be forcing the sector to use this. Aluminium magnesium, by the way, it's increased a lot, especially in the automotive sector, and it's recommended especially due to problems regarding weight again. But as I said, aluminium lithium is quite expensive, but the aluminium magnesium is cheaper, but the fatigue features or the fatigue specifics need to be analyzed. Safety health monitoring. There are certain sensors which you place on the aircraft, especially during the manufacturing phase, and via those, it could be temperature sensors, it could be all kinds of different sensors. And what is happening within the aircraft throughout all the life cycle of that aircraft, you're able to follow due to those sensors. What does this enable you to do? Well, there are, of course, many factors which you have taken into consideration before. You have increased them, or you have played with the necessary values. But when you put these sensors, then you really, really are able to observe what takes place in reality. Because you know that D level, A level, B level, all aircraft goes through some kind of maintenance, all of them for sure. But with these sensors, you're able to observe exactly what has taken place where. And as a result, of course, you're able to do this throughout all the life cycle. This is actually not a very new technology. It's been used for the last decade, especially in A420, the wings of A420. But unfortunately, this has not become very widespread with aircraft, with airplanes. The main reason being that it's very expensive, and secondly, because the companies that work in this field don't really actually present very good solutions. Yes, they do obviously work in this field, but they don't really present solutions which are very suitable to this sector. But I believe that serious work is going to be held in this field so that sensors are actually fitted at the manufacturing level, for example, at the manufacturing phase.
Dolayısıyla isterseniz bir conclusion'u, bir toparlarsak.
So, if we are to conclude,
Kesinlikle ağırlığı kompozit kullanarak azaltabiliyoruz.
yes, we're definitely able to decrease the weight in aircraft by using composite material. Nobody can say anything against this. And assembly line. For aircraft, assembly line is the most important phase, and it's very important that we do not lose any time or money at this phase, at the assembly line. And the decreasing weight should definitely be not at the assembly phase, but at the phases before. I try to share my experiences with you. Thank you very much for listening to me. Thank you very much for your attention. And if you have any questions, I'll be more than happy to answer them. I think he's asking MakerMaster tool. MakerMaster. If you look at it to the internet, yeah, just write it down in Google and you'll see it. It's a very beneficial. It's quite useful. But as I said, it's not a tool that's very easy to use. You talked about a test regarding the lightning strike. Where is that test conducted? In the United Kingdom, that's where we had the lightning strike test. 2 million amperes of current is actually subjected to that field, and you see how it burns. And then you take that field which has been burnt, that whole field, you measure how deep it is, and if you have any kind of, let's say, copper mesh or any kind of other precaution, you see how that has been affected as a result of that. Then this structure, especially our friends that work in the analysis department, they see whether they will be able to save it or not, whether they can save the part or not. Of course, the aim here is not to save that part until its normal life cycle. What we try to look at is whether the aircraft will be able to go to the nearest airport safely. I'm sorry. Composites are with fire, composite material and their relation to fire, I think he asked. All composite materials give different reactions to fire, but for each department, for each part in the airplane, in the aircraft, they all have different regulations. For example, we worked in the cargo door, and that was where the electronical equipment and the baggage department, the luggage department, we actually segregated. And the wall that we constructed, we actually constructed it from composite material, and we actually made sure that there was going to be any fire, it wasn't going to be affected by fire or even smoke even. So each part in the aircraft actually has different requirements. It's easy to work with foreigners because they have their standards for each part of the aircraft, which is what we need to do also. We need to know what the requirements of each zone or each department is. Fire, for example, obviously it's not acceptable for any part of the aircraft. Glass fiber, we usually cover it with, there is special glass fiber, and this actually prevents the fire from growing or from spreading. So glass fiber is quite a good solution regarding regarding fire. Titanium, I think. Sometimes we use steel. We try not to. Why do you use steel? I think that's the main question, I think, for fasteners. Because sometimes with steel fasteners actually do give a better performance for certain parts. Now, corrosion is such an issue that each part the way they fasten or the way they connect to one another is very, very different. When you're going to choose a fastener, there are different heaps and heaps of different forms of coating that they may actually have. Let's say there is something that we term as electrical corrosion, for example. The minute that you connect two different materials, there is some kind of electrical conductivity that takes place, and they begin to, if I may say so, eat away at each other. So and we have such a guide, we have a book this thick, and which material cannot come together with which material, which coating cannot work with which fastener, etc., etc. But corrosion is an extremely, extremely important issue in aircraft. And with composite, we say that we have solved the problem of corrosion, but because we are not able to get rid of metal, and as long as we continue to use metal, even if we use composite material, that on its own, it's not going to be enough to solve this problem of corrosion. Otherwise, the product that you have, the life cycle of the product actually becomes shorter. Is there such a standard? There should be a military standard. But military standards usually write down the procedures. They will give you the method, or they will give you the route. They will tell you how you should do it, but it will not give you the values, for example. The companies need to, what we term as know-how. Each company has their own know-how, and they don't usually share it. But because we work with Airbus, we have to use their information. That's why we took it off them. But actually, I think it should be shared. I'm not saying you need to share all the documents, but you can, for example, write a book. But this knowledge should be shared. That's my opinion. Springback. How can we solve the springback problem? Usually with springback, when you're doing the stress analysis, one of the issues that has a most impact on is the stacking problem. And when you put your stacking seconds, you will find where the problem is, where the deflection is. And sometimes it may not be just because of production or curing. Sometimes it's actually how it's been put together. So our colleagues, our friends who work in the analysis department, they will see it. And even though sometimes, because of different reasons, there can be an increase or decrease, and we use composite tools at first stage, and after the first stage, before you move on to the normal phase, then we move on to the normal tooling phase. But of course, some kind of software can be programmed. But especially, once again, I would like to say that with composite material, it is always different from one another.